Hello and welcome to our virtual lunch and learn today. We are going to be talking about motion analyzer software today. My name is Rachel Green. I'm the digital communication specialist here at McNaughton-McKay Electric Company. And presenting for us today is Gary Smith, systems engineer out of our Greenville, South Carolina location. Welcome, Tom and Gary. I see you guys in the comments already. Out in the comments section today, ready to answer your questions, is Tom Joy, systems engineer at our Madison Heights, Michigan location. We will also have a Q&A portion at the end of Gary's presentation for him to answer your questions in more depth. We'll be getting started here shortly, but we'd like to allow a few minutes for attendees to join us. As you come in, let us know where you're tuning in from in the comments section. Get to know one another there. As we continue to socially distance, we're happy to be able to provide these sessions here on YouTube, making it possible for you to join us from the comfort and safety of your own homes and offices. You can always view recordings of previous virtual lunch and learns on our YouTube channel under the Virtual Lunch and Learn playlist. And we will be continuing this series as we do on Wednesday at noon every week, so be sure to join us on your lunch break. Welcome, AJ. Thanks for joining. For anyone just coming in, welcome to our virtual lunch and learn motion analyzer software. Let us know where you're joining from in the comments section. We will be looking for questions while our presenter, Gary Smith, talks to us about Rockwell Automation's free Servo and variable frequency drive sizing and selection tool, motion analyzer software. Our specialist, Tom Joy, will be available to respond to your questions in the comments as we go through. And we'll also have a Q&A segment at the end of Gary's presentation to address those questions and to allow some time for follow-up questions if you have them. If you'd like to reach out after, or if you have further questions for Gary, you can send us an email at the email address there on the screen, macandmaclive@macandmac.com. Be sure to let us know the name of this session so that we can get your questions to Gary and he will reach out to you directly. Welcome, Jody and Leanne. Thanks for joining today. And Pete. All right, it looks like we have a number of attendees joining us now, Gary, so I'm going to pass it over to you.
All right. Well, thank you so much, Rachel, and thanks to everyone for joining today. My name is Gary Smith. I'm a drives and motion specialist for McNaughton-McKay Electric in Greenville, South Carolina. Today, we're going to talk about Rockwell's cloud-based servo sizing tool called Motion Analyzer. This software can be accessed at motionanalyzer.rockwellautomation.com. And first, a little bit of quick history. The sizing software that we've used for many, many years is what we refer to as Motion Analyzer 7.2. This is a PC-based or desktop software that has been in use. Unfortunately, it's being phased out, and it no longer supports all of the current generation products, including some of the Encompass partner products. Instead, we've moved to a new platform called Motion Analyzer Online, and this is the software tool that I use every day to size servo drives, variable frequency drives, motors, and even electromechanical products. It's very easy to update, and when it's updated, the rollout goes to everybody all at the same time. So everybody's always using that same software tool. And since we can do those updates, we make sure that we always have the latest, greatest products, both from Rockwell and our Encompass partners. One of the other features of this software is the ability to collaborate with others. So when you create a project, you're going to be able to share that project at varying levels of access. And you're going to find that that's very, very helpful, both collaborating with coworkers and also sharing information with technical resources to provide assistance for you. One of the nice things about this, as Rachel mentioned, is it's a free software just like Motion Analyzer 7.2. Also, there is going to be an accompanying software, a desktop utility for the Motion Analyzer. It's under development now, possibly out next year. So if you don't have internet access, you'll still be able to utilize this sizing tool. We have a limited amount of time today, and Motion Analyzer offers quite a few different features. So we wanted to make sure that we hit the high points, covered as much ground as possible. So we put together 5 different short videos covering basic navigation, how to create a project, how to add an axis, how to add a second axis, and then how to create a shared bus that will size a power supply for us and accessories. So all of these videos are edited for time just to make sure that we stay on track and get through in our allotted time today. But don't hesitate. Another thing that Rachel mentioned is we will have the ability to have this presentation saved on our YouTube channel, so you can go back at any time that you'd like and review all the steps that we take today. So first, we're going to talk about basic navigation. What does the screen look like, and what are the available options? So again, motionanalyzer.rockwellautomation.com is what you're going to use to access the site. And this is what you're going to see. You're going to be able to create a logon by going into the upper right-hand corner, filling out your information, including your email address, and you will receive an email that will help you complete the registration process. In our example today, I've already have a logon for our group that I will be using, so I'm going to go ahead and submit that logon. And from here, you're going to see your profile section. When you go to view profile, this is where you're going to be able to change your password if you like, and also create all the information relative to your personal data. We talked about the ability to share project info. You can take a look at what's shared and what access level, and if things are shared with you, you'll get notifications. If you want to change your user units, this is how you do it. So you can use metric or imperial units or a combination, whatever you choose, and then hit Save Settings at the bottom. The Motion Analyzer logo at the top will take you back to the main screen. So first, we'll talk about some of the products that are supported here. If I browse for the drives, you'll be able to see all the different Kinetics products as well as PowerFlex products. If I go back, I can look at our motors. So you're going to see all of our current generation of VP motors, food grade motors, MP series motors, medium inertia, even induction motors. So all of the current generation products are there. And one of the other really nice features of the software is the ability to use Rockwell and Compass Partner mechanical products, most common of which are the servo gearing products. So here are just a couple of examples, and you can see the wide array of different options that we have that we can configure and use as part of our sizing. You can hit Motion Analyzer to jump back, or I kind of just jumped over to the next section as we're going to talk about some of the tools that are available in Motion Analyzer. So one of the things that you might want to know is the compatibility of something. So if you know a motor and or a drive and you want to know what motors or drives are compatible, you can just enter that information here. So if you know the full part number, you use the left-hand column. If you don't, you can build from the right-hand column. So we picked a VPL B1153F motor, and by using this, we can find out that the only drives that are suitable for use of that motor are the Kinetics 5500 and Kinetics 5700 servo drives. Jump to tools. Let's say that you have a drive and motor selected and you want to know what performance to expect. You can create the speed torque profile by simply putting in the voltage tolerance, ambient temperature, and altitude. and select the motor and amplifier, and it will show you exactly what you can expect from both a continuous torque, peak torque, and RPM standpoint. So we're going to create our motor. We'll pick the same motor as before. We're going to add a Kinetics 5700 dual axis amplifier, which is a 2198-D020. Once we have these items selected, we're going to generate our graph. And there you have it. You can see the continuous torque curve, the peak torque curve on the outside, as well as available RPM. And we did that without having to size from scratch. Our library is where we're going to find all of our project data. So when you create a project to work on, you'll see it listed here, and it's sorted by when it was modified. You can also go here, and this is where you're going to share access. So if you click on action, you can see that there's a share tab there. I could create a project here, but we're not going to at this time. As you go through, we're going to build different motion profiles. We're going to add different mechanical products. You can save these, and that will allow you to reuse them in the future without creating them from scratch each time. So therefore, saving you a little bit of time. I'm going to return to the main screen, and that completes the main overview. So now you have a little bit of an idea of some of the features that are there and how you move around. We're going to create a new project. I'll just jump right into that. So you can create a project in one of two ways. You can start a new project or create from an XML. So you can save a project as an XML. That's really the only way to save offline. And you can re-import it into your library. But we're going to use a new blank project. This is where you're going to give it a name, and this is exactly how it's going to be listed in your library when you pull it up in the future. And you can give it a product description to just provide a little additional detail for yourself. And we're going to create that project. The architecture overview is pretty much your main screen that you're going to see for sizing purposes. There are a few other things we can point out here. Preferences, we have the ability to create a project report, and you can fill in this information to the best of your ability, and it will make for a nice report when all is said and done. Power analysis and bill of material are going to be blank at this point because we have done no actual sizing. And if we look at our project report, it's going to be pretty sparse right now. It's only going to have the basic information that we entered. If I jump back to the overview, you can see where we would add a bus or add an axis. I just wanted to point out a couple other things here. This is where you would export as an XML. You can also take a snapshot since we're always saving our progress throughout. If you ever wanted to return to a point in time, you could take a snapshot and then restore from that snapshot. You can also see who your shared users are here as well. So we've started our project, and now it's up to creating a new axis. So we have put together an example application just to kind of give you a feel for how you would generate sizing or develop sizing for an application. In our application, we are going to have a pick and place gantry. So we're going to have a horizontal axis called the x-axis. We're going to have a vertical axis called the z-axis. So our gantry x-axis is horizontal, and our mechanism in this case has already been specified for us. So there is a belt drive with a pulley and a belt, of course, and a gearbox. Our belt drive has a 47.74 millimeter pitch diameter pulley, which means that for one rev of that pulley, we travel 150 millimeters. In our application, We have tooling mass. Everything that we're moving around weighs 100 kilograms. In addition to that, when we pick a part that we're going to move, we're going to see an additional 50 kilograms of payload. So sometimes when we're moving, we have 100 kilograms. At other times, we have 150 kilograms. We're going to assume a 0.1 coefficient of friction, which is a very relatively conservative value that we commonly use. The gearbox that's part of the actuator is a 5-to-1 gearbox with a 90% efficiency. Based on that combination of gearbox and actuator, the manufacturer has specified a limitation of no greater than 1.5 meters per second. We're also asked to provide high stability and dynamic response. Well, two of the things that we would normally do are try to ensure minimal backlash in the gearing and minimum compliance in the belt. Unfortunately, those things have been decided for us. So the feature that we can take a look at is the inertia mismatch between the load and the motor. So in this case, we'll try to limit that inertia mismatch to a value of 10-to-1 or less. If you look at the bottom of the screen, you'll see a 6-second cycle. So this is in regards to just the x-axis, and you're going to see that we are going to advance and retract 2,000 millimeters in 1.5 seconds, and we have a couple of dwells. When we're advancing without the part, we have a 100 kilogram payload. When we're returning with a part, the total payload is 150 kilograms. So now we're going to jump into the sizing, and you'll see exactly how we enter all of that information. So we're at the architecture overview where we were before. We're going to click on Add an Axis. We could add from the library, but we're going to create from scratch, and we're going to add a blank axis. First thing you'll see here is a pencil. Anywhere you see a pencil, that means you can edit something. And we're going to give it a more descriptive name so we know that we're dealing with the x-axis here. Click on View Details. You'll see that they're empty right now. There are a few other small icons here that we'll talk a little bit about in the future. But the Edit button is what allows us to get started on creating our overall sizing. By default, we pop up, we have a rotary axis. We know that this is a linear axis, and there are several application templates at the bottom that may be better suited for applications. However, linear is all we need here. So we're going to continue to our profile editor. So we have a start condition. In this case, everything is basically starting at the 0 position, and our inclination is 0. If we had a vertical axis, we would change that to 90 degrees. And we're going to get started. Just as a reminder, we're making those 2-meter moves in 1.5 seconds, and we have the varying payload. And don't forget the coefficient of friction. So we're going to start off by adding an index. By default, that index is a 1/3 trapezoid, which means 1/3 of the time we're accelerating, 1/3 constant velocity, 1/3 decel. We know that we have 1.5 seconds to move. We can change our units. I could have entered in meters, but I will put in 2,000 millimeters. And as soon as you hit enter or click outside of that box, that profile has been saved. If you look at the velocity on the y-axis there, I hover over to the left. If you look right there in the red, you can see that it's 2 meters per second. Well, that exceeds our limitation of 1.5. So there's a positive velocity limit I can use. I'm going to type in 1.5 meters per second. And just like that, it has changed our profile. Now, the next part was a 1.5 second dwell. I just simply click on the dwell, change an incremental value to 1.5 seconds. And I'm going to add our return move. It's going to be another 2,000 millimeter or 2 meter move in 1.5 seconds. However, in this case, our direction is reversed, so we are going to enter a minus 2,000 millimeter move, and when we do, you'll see the velocity profile go bipolar or go to the negative direction. Again, if I hover over that section, I'll see that I'm at minus 2 meters per second, which is greater than our allowable velocity. So we're at minus 1.5 for our limitation. And we have one more dwell to add in of 1.5 seconds. So our profile for velocity and position is complete, but we have to add our load values. So I'm going to add a mass value, and this is one of a couple different ways you can do this. I'm using the variable permutation, and what we're going to do is we know that in our profile from 0 to 3 seconds, we only have the tooling because we have not picked up the part yet. So I'm going to add 100 kilograms, and you'll see it highlighted everything from 0 to 3. And if you were to look to the left-hand side under additional loads in that area, you'll see 100 kilograms. Now I'm going to add the mass for after the part has been picked up. I'll do the same thing with the variable from 3 to 6 seconds. And I'll change my mass to 150 kilograms. And again, at this point, after we apply the changes, if you were to hover over that section, you would see that the additional load shows up as 150 in that segment. This is also where we add our friction coefficient. This is constant all the time. It's always 0.1, so we're going to leave that value there and apply the changes. There is an alternate method for entering those payloads. I can click on the individual indexes, and on the right-hand side, which may or may not be hidden on your screen, you can enter the load value there. Just make sure that you don't add load values twice because they will sum together. And you don't want to add more than once. So we have completed our entire profile, and we're going to continue to our linear mechanism. You get a running tab of exactly what's happening under application requirements. You can see that we have a peak linear speed of 1.5 meters per second, and you have forces in newtons. We're going to go ahead and select a user-defined mechanism instead of an Encompass partner product. And you'll see that those application requirements are still going to be the same, but we're going to pick a belt drive. And you can see it's creating a new mechanism, and you want to make sure that it fully accepts that creation. Once we're done here, we can save this mechanism. We will not do that in this demonstration. You can give it a unique name, add table mass, add belt mass. We're not going to do that at this time. This is, however, very important. We need to add that pulley diameter of 47.74 millimeters. If we had the inertia data and the frictional data, which is very common in the manufacturer's data, we would do that. There is an inertia calculator I wanted to point out there. The friction value can be very important, especially when you have a very, very small motor. But for our purposes today, we're going to leave that blank. But obviously, if you have the information, the more data that you can put in, the more accurate the sizing is going to be. We're going to continue to a transmission. We're not going to be adding a Rockwell Encompass partner product. But I did want to point out here that now our requirements are in rotational values. So we have an RPM requirement of 600 and a peak torque in Newton meters. So we're not going to add those Encompass partner gearing products, but we are going to accommodate for this unknown 5-to-1 gearbox ratio by adding a spur gear. So I just clicked on the plus. You can see there's a pencil, which means that we can edit. I'm going to change the ratio to 5-to-1. We know that the efficiency is 90%. And again, if we have the published data of friction inertia, we would add that here. If you're using a Rockwell Encompass partner product, all those values are already taken care of for you. If we were to add an additional gearbox, we would go to this screen. You can see where you can add by a complete catalog number or select a family of gearing products that you could use here. For now, we're going to jump straight to the motor. If you note the application requirements, before we had the 600 RPM requirement. Well, now we've added a 5-to-1 gearbox, so we know from the motor standpoint, we need a motor that will achieve 3,000 RPM, even though the torque requirement is less. So we're going to pick a motor, and if we knew the motor model number, we could add that here. However, we're just going to pick a family that we can use, and that'll be the VPL series of motor. And we're going to allow the software to do what it does to help us select a solution. Next, we're going to pick a drive. So we can't look at application requirements because we don't know specifically which motor is going to be selected. So we're going to pick a voltage to use, wait till the power data is saved, and then we're going to pick a family of drives, which is going to be the Kinetics 5700 servo drive. Wait till that's saved. You can see that the family is selected. And now we're going to allow the software to do what it was designed to do. We're going to do a solution search. Once we click on the search tab here, it's going to go through every combination of VPL motor and Kinetics 5700 drive to find the best fit. If we had an Encompass partner product in there as well, it would go through all the different potential solutions there as well. So we get 10 results. The top one is usually the best solution, but not always. If you look at our inertia ratio, you can see it's above the 10-to-1 that we wanted to target. So even though it's the best match, it may not be best for our application. So I can actually sort on that column. And I'm going to look for the inertia ratio, the lowest cost solution that is under a 10-to-1 inertia mismatch. If I look down here, the VPL B1153F motor with the D020 amplifier is going to be our best solution. We've saved that. And we're going to go to our analysis. So we get a very good looking speed torque curve. We have these red dots. All the red dots signify the peak torque and RPM requirements for each of those profiles, each of the individual indexes we created. The red dots have to be beneath the red peak torque curve. And there's one green dot, which is the RMS value of speed and torque. And that has to be under the green continuous torque line. If you look at the summary tab here, we have all green bars, which is very good. You can go to the drive and motor tab, and it tells you exactly what the application requires of the drive's capability in the right-hand column, and in this case, the motor. Once you have something selected, you can use the size up and size down icons to move around. In this case, we size down by 1, and that is clearly not going to work for us. We're very, very close to the peak torque curve. So we're just going to size this back up and stick with the 1153F motor that we originally came up with. I'm going to apply that. So basically it's saving that particular combination to your project and to that axis. And we're going to configure components. So here, we just know that the 1153F is basically a series of motor, but there are several more characters that need to be filled out to complete the part number. We are going to pick a SIL2 safety encoder with no break, and you see a pop-up on the right-hand side there. You can download that motor directly from Motion Analyzer here. So we've selected the motor, and now we're going to pick a dual axis amplifier with advanced safety support, which is the ERS4, and we have completed the sizing of our first axis. So we are going to immediately jump into our next axis, which is going to be a Z-axis vertical. The mechanism here is very similar to what we used before. You'll see that it's the same pulley diameter, probably a different stroke length, but it also has the same 5-to-1 gearbox, and it also has the same limitation of 1.5 meters per second. As I mentioned, it's vertical. In this case, we only have 5 kilograms of tooling, but we do have 45 kilograms additional payload when we pick up the part. We also have the same identical 6-second overall cycle time, but these are going to be synchronized. So when the x-axis is moving, the z-axis is stationary. When the z-axis is moving, the x-axis is stationary. So to accommodate for that, if you remember, we started off with the x-axis by immediately moving our 2 meters in 1.5 seconds. So here, we're going to be idle or dwell for our first 1.5 seconds. At that point in time, we're going to begin making our lowering and raising moves to pick up and drop off the part. We're going to travel 1,000 millimeters, worst case, in 0.75 seconds. And that payload will vary between 5 kilograms and 50 kilograms. So this is essentially where we left off after creating the x-axis. If you view details, now we have some data. So we've populated all these different areas. We have the exact motor and exact drive that we want to use. So we know the mechanism is very similar to before. So let's duplicate the x-axis to make it a little bit easier to add our second axis. So we'll change that to z-axis by clicking on the pencil button. We'll jump right to edit. And when you take a second here, you'll see everything populates across the top. You see all these green check boxes, meaning all these different things have already been taken care of. However, one big change we know of is the profile is completely different. So I could modify those individual profiles, but for now, just as a refresher, we're going to clear everything out of there. And as I mentioned previously, since we do have a vertical orientation, we need to change the inclination to 90 degrees. As a reminder, that's what we're looking at. The 1 meter moves in 0.75 seconds. First, we're going to add that 1.5 second dwell to allow the x-axis to make its move. And then we're going to add a 0.75 second move of 1 meter. We're going to start out going downward. So that is a -1 meter move. And we're going to come right back up with another 0.75 second move of 1 meter as well. Don't forget, if you hover over these segments, you'll see that they are also at 2 meters per second, which exceeds our 1.5 meter per second limit. So we're going to put in a velocity limit of 1.5 for the positive move and negative 1.5 for our downward move. We're going to dwell for 1.5 seconds for another horizontal axis move. And then we're basically going to repeat what we did before, making two 1 meter moves, 0.75 seconds each, with the appropriate velocity limitation. And that completes our 6-second total profile. Now we're going to add our load values here. In this case, we're going to use the constant permutation and put in our 5 kilograms of tooling because we know that this tooling weight is there all the time. However, we're going to use the segment tool to add in our additional 45 kilograms. So when we're raising with the part there, we're going to add 45 kilograms. And if you look at the additional load mass of 5 kilograms, it's always there, and a segment load mass, if you look within that window as I hover across here, you'll see those values change from 0 to 45 kilograms and then back to 0 here. So I'm going to go ahead, add another 45 kilograms as we're holding that payload and the horizontal travel takes place. And then one final 45 kilogram load as we lower the part to the drop-off point. And again, one more time, if you look at that, as we hover over those areas, you'll see exactly where that payload is, the total accumulated load. We jump into our actuator, and as before, it's saved, right? We have the same data as before, same pulley diameter. Again, if we had the inertia and friction, we would enter it. We have the same gearbox, showing a spur gear of a 5-to-1 ratio, 90% efficient. We are not going to go to the gearbox segment because we know we're not adding an additional gearbox. We still have the VPL family saved there, but we're going to eliminate the specific motor because we're going to allow this to search the entire family. Same thing with the D020, we'll remove it, but leave the Kinetics 5700 drive family and wait till it says drive selection saved. Jump to our solution search and let the software do what it does. So again, the top solution is usually the best match. We will go ahead and select that. And jump to our analysis. So at first glance, this looks like it'll work. The red dots are within the red line. However, personal preference, we try to keep the peak torque to no greater than 150% of the continuous torque. So I'm going to bump that motor size up. You'll see this motor does not work for us. One more time. We're at the 1153F, which just so happens to be the same motor we used on the horizontal axis. Everything looks great there, so I'm going to apply it. Wait till it says it's saved. Go to configure, same steps as before. The only difference on this motor, we're going to do the SIL2 encoder, but we need a brake on this motor as well. So you can see the different columns there and the different features that they offer that will help you build out that part number. And as soon as you have that part number selected, which is going to be a QJ14AA highlighted there by me, and don't forget that your 3D model is there in the right-hand column. And we'll also pick that advanced safety version of the Kinetics 5700. So almost finished. So we have completely sized two axes of motion. We have the horizontal axis with a servo motor and amplifier. We have a vertical axis with a servo motor and amplifier. The Kinetics 5700 drive works with a shared bus system. So there is a separate component called a DC bus power supply. And we are now going to create a shared bus, add the axes that we've created, the amplifiers, to this shared bus, and it will allow us to size that power supply and any required accessories. So you can see our x-axis and z-axis. We're going to add a new bus here. We'll go to the pencil and we'll give this a unique name, which is not necessary at all, but could be if you had multiple configurations in what we call clusters. And we have to physically move these axes to that bus, but it's very simple. You click on the icon and then you click on move to the bus, and that's it. It really is that simple. Move to bus, move to the DC bus power supply 1. So when we created these axes, we created them independently, right? One after the other. And each one selected a D020 dual axis amplifier. So dual axis is just what it says. It can control two different motors. So right now we have two different dual axis amplifiers. So we're going to use the merge feature. And again, just that simple. I click on the merge button, and I've added the X and Z axis to one single dual axis amplifier. When we go to power analysis, this is where we're going to size that DC bus power supply. Go to our setup tab, and you're going to get some great information here on exactly what's going on in your application. So if you scroll to the bottom, you can see what's going on with the velocity and power consumption for each of the two axes, and you can see how they're offset in time because we synchronized them. If I update the graph, you're going to see what's required of the power supply. So over time, over that 6 seconds, you can see we have a couple segments there that require 3 kilowatts of peak energy. So we go to our power supply summary section. You can see nothing is selected at this point. I can allow the software to select for me by doing auto, or if I know what part I want to use, I can select manual. I'm going to leave everything at auto and hit the calculate button. And now you know exactly what's required. It has selected a P031 bus supply, which is the smallest module. And it has also selected a shunt module for us, meaning that there's quite a bit of regeneration going on in the application. So we picked a 400 watt resistor. And if you look at what was required of the bus, the power supply section, the requirements are very light. We're only requiring 4.5 amps out of 31.6 amps peak. And you can see that we're requiring 87 amps out of 400 watts in that resistor. And our profile, if you look at the voltage versus current, you can see when it's regenerating. You can see when current is flowing in the positive direction versus negative direction. So just a phenomenal analysis of exactly what's going on. Bill of materials, we've pretty much picked everything out. If you look at it by axis, it still says that there's a DO20 for each one. But that's a little bit misleading. If you look by type, it's going to show you basically the 5 components that we selected when we did our sizing today. And our project report's going to have a lot more information now than it did before. And you can export this to as a PDF when you're done. But for now, as we scroll through, you'll be able to see the x-axis, the motion profile, what the performance looks like, what the speed torque curve looks like. The z-axis is going to offer the same thing. And eventually you'll see the effect on the power supply components that we selected as well. So again, a very high-level overview of what the capabilities are in Motion Analyzer. But I would like to leave you with a couple of final comments, basically to make your introduction a little bit easier. First off is if you are done editing and you've come up with a solution, you want to make sure you don't overwrite that solution because we're always saving whatever changes take place. So take advantage of the ability to duplicate your project or axes, or use that snapshot tool so you can always return to a known point in your sizing. There are quite a few calculations going on. Some of them are pretty intensive and some take a little bit of time. So make sure whenever you make a modification to a screen, please give it time to fully complete those calculations and populations and saving whatever data is being manipulated before you advance to the next screen. If you advance too early, you may lose the work that you have created. As I mentioned, some of these things are pretty intensive, time intensive, the number crunching that goes on. However, if you get the sense that you're not making progress as you're waiting, don't hesitate to refresh your web page. Make sure you utilize the share feature at the appropriate access level. So by default, if you wanted to share a project with a coworker or a distributor motion specialist or Rockwell, the default is a read-only share. And with that, you can't even really dig into the details of the motion profile. So I suggest that you save as a minimum or share at a minimum as a read and copy access. That will allow whoever's looking at your project to copy their own version of it, which they will be able to modify. And there's also full read-write access as well. And the one final thing I'll leave with you is explore. This was a very high-level overview. I could have spent this amount of time on just motion profiles and how to enter data on that screen. There are just a wide array of things that you can do. If you noticed all the different templates for the different applications, if you have something that's better suited than just a straightforward linear or rotary, make sure you take a look at those things. And one final time, to access this software, motionanalyzer.rockwellautomation.com is where you'll gain access. If you need assistance, again, don't hesitate to reach out to your distributor motion specialist. But if you have to contact Rockwell, their email is motionanalyzersupport@ra.rockwell.com. And if you are asking questions about a given project that you're working on, you will want to share that project, again, with a minimum of read copy access to that same email address. And that is pretty much it for the material I had to cover today. If you need anything else, again, don't hesitate to reach out to your specialist or email us at macandmaclive@mc-mc.com. Just please make sure you reference Motion Analyzer to make sure we get you the data applicable to the presentation of interest to you. And with that, I think I'm going to turn it back to Rachel and see if there was anything in the chat window that needed to be addressed.
Thanks, Gary. We don't have any live questions right now, but I'm going to give just a few minutes to see if anyone has any follow-up questions for you. While we wait, I'd just like to remind you once again, like Gary said, you can email us at that email address on the screen if you have questions after the fact, or if you would like to reach out and you're watching this as a recording, you can still reach us at that email address and just reference the session and we'll get your question to Gary. And I'd like to thank Tom for being our resource out in the comments section. It does not look like we have any questions at this time, so we'll go ahead and wrap it up. Thank you to all of our viewers and attendees today for giving us your time. We hope this session was informative and engaging for you. Remember to subscribe to the McNaughton-McKay YouTube channel for more industry content like this. And we look forward to seeing you again live next week. Thank you so much. Thank you, Gary.
Thank you.